Thank you for attending this presentation by David Avilés from the Autonomous University of Baja California and myself, Ixbalan Torres from the University of Guanajuato. Dark fermentation is a fermentative conversion process occurring when methanogenesis is prevented in anaerobic digestion, a process through which bacteria break down organic matter from, for example, wastewater, in the absence of oxygen. Dark fermentation is a complex hydrogen production process in which several malfunctions or imperfect behavior may appear during normal operation. Such malfunctions can be detected by means of different strategies of fault detections. Even if in recent years some works have been devoted to estimate the state of biohydrogen production processes, to the best of our knowledge, there are no works devoted to detect variables related to biohydrogen production processes in the occurrence of faults. The classical model-based fault detection methods consist of a residual generator and a residual evaluator that make the fault detection decision with the aid of a residual evaluation function, considering fixed or adaptive thresholds. In this work, we propose a Luenberger observer for a hydrogen production bioreactor in occurrence of sensor faults. Using the bioreactor model, we will present a residual generator from measurements of the hydrogen flow rate and the available input flow rate to detect the occurrence of sensor faults despite the influence of the inlet glucose concentration. Additionally, the observer allows to estimate the glucose and the biomass concentration in the bioreactor. The biohydrogen production dark fermenter is modeled in liquid phase by a set of 8 ordinary differential equations. The state vector includes the concentration of the glucose, the biomass, 4 volatile fatty acids, carbon dioxide, and hydrogen. The biological kinetics are modeled by 2 monotype reactions. The mass transfer from the liquid phase to the gas phase is modeled using the film theory. In the gas phase, only the carbon dioxide and the hydrogen dissolved from the liquid phase are modeled by an ordinary differential equation, respectively. The total biogas produced is the sum of the carbon dioxide gas plus the hydrogen gas produced. The measured output is the hydrogen flow rate produced by the dark fermenter, defined in this equation. Nevertheless, in the case in which a fault occurs in the sensor, the measured output is complemented with a sensor fault function f sub index s. The dynamics of the hydrogen flow rate are related to the concentrations of glucose, biomass, and hydrogen in both liquid phase and gas phase. The state vector set is therefore defined in this way. A 5-order nonlinear model is then proposed where the input flow rate is considered as control input and the inlet glucose concentration is considered as a disturbance. By linearizing the previous nonlinear model, the following 5-order linear model is calculated. Nevertheless, since the state variables related to the hydrogen are linearly dependent, the pair AC C sub index C is not observable. In order to achieve the observability condition, a new state vector considering only the glucose and the biomass concentration as well as the hydrogen flow rate is proposed. Thus, in this way, a linear state space model with pair AC observable is defined. The dark fermenter model includes a set of uncertain parameters related to the hydrogen dynamics, environmental temperature, the hydrogen mass transfer coefficient, some pseudo-stoichiometric coefficients, the hydrogen mass, the maximum specific growth rate of the microorganisms, and the Hall saturation constant. These parameters are grouped in vector P. The environmental temperature is considered to vary between 278 degrees Kelvin and 303 degrees Kelvin, while the rest of the parameters are considered to vary between plus minus 10% of their nominal value. W bar belongs to the domain D subindex W for W star between 0 and 25 grams per liter. This way, the uncertainties of matrix A are inside a two vertices polytope. Each vertex is calculated from the minimum and the maximum variation of uncertainties of vector P and disturbance W bar, respectively. The residual generator is therefore defined by a Lemberger observer here, with residual defined as the difference between the measured output and the estimated one here. In this residual generator, the observer gain L has to be designed. By defining the estimation error as the difference between the linearized state vector and the estimated linearized state vector, its dynamics are given by this ordinary differential equation. Of course, the residual depends on the estimation error. In order to compute the observer gain L such that the convergence of the estimation error to a neighborhood of the origin is assured, even in presence of parametric uncertainties and the external disturbance, the H infinity norm of the transfer function matrix G is minimized by solving the following semi-definite optimization problem for each vertex of the polytope describing the uncertainties of matrix A. In addition, the poles of the observer, the Lemberger observer, are placed inside the stability region formed by the intersection of a bar described by this LMI, a semicircle center in the region described by this LMI, and a conic section described by this LMI. Due to the effect of the input glucose concentration and the parametric uncertainties of the vector P on the dark fermenter dynamics, the residual generated by the Lemberger observer will not be exactly zero, even under a fault-free condition. Therefore, we consider the following residual evaluation function, which measures the average energy of the residual signal R over the time interval T minus delta T to T. On the other hand, the fault detection threshold is defined as the product of the H infinity norm and the supremum average energy of the sum of the unknown input and the uncertainty effect. Thus, if the residual evaluation is larger than the fault detection threshold, then a sensor fault has occurred. Else, the hydrogen sensor is fault-free. In order to demonstrate the feasibility of the fault detection strategy, the residual generator was simulated in MATLAB. The measurements of the hydrogen flow rate and concentrations of the glucose and the biomass in the dark fermenter were computed by simulating the dark fermenter mode. The semi-definite optimization problem was solved using CVX with the SDPT3 solver. The ordinary differential equations were solved by using the Steve solver OD15S. The reduced nonlinear model of the dark fermenter was linearized around the following operating point. To simulate the dark fermenter, the following vector P modified was considered. For simulations, input during 64 days from a previous work were considered. As mentioned before, the input flow rate is a control input, while the inlet glucose concentration is an unknown input. 3 scenarios were conducted for the validation of the fault detection observer. The first one considers the case with a noise variation of 1% on the hydrogen sensor. The second scenario considers a noise variation of 10% on the measured output. In a third case, a noise variation of 1% plus an offset of 25% are considered. This slide shows the estimation results by the Lemberger observer. as can be regarded in the evolution of the hydrogen flow rate produced, the estimation by the observer converges to the flow rate by the model in the periods of time when the sensor is fault-free. Here, here, and here. Otherwise, in the periods of time when the sensor presents a fault, the estimation by the observer does not converge to the flow rate by the model. Here, here, and here. On the other hand, as can be regarded in the evolution of the glucose and the biomass concentrations in the dark fermenter, both estimations remain close to the concentrations by the model all along the simulation, demonstrating the robustness of the observer design. In this slide, we can see the evolution of the residual and the dially evaluated average energy of the residual. The fault detection threshold is shown in the red dashed line and has the value of 0.63. As can be regarded, in the periods of time when a fault occurs in the hydrogen sensor, the residual is larger, here, here, and here. And its dially average energy is larger than the fault detection threshold, here, here, and here. As conclusion, simulations showed that the observer is able to correctly detect faults in the hydrogen flow rate sensor and estimate the concentrations in the dark fermenter. The fault detection strategy proposed is robust against parametric uncertainties and an external disturbance. Thank you very much for your attention.